I'm sorry, maybe I'm not quite well visible, but at least talk is visible very well because it's very bright morning today and sun just goes from the side to my face. So, and I'm very much pleased by Shigehiro-san for this invitation, by Shigehiro-san to invited me to this seminar. So, and I would like to talk about some analytical and numerical simulations. So, there are some analytical approaches and also numerical simulations which confirm or partially disprove them. So I will show you later simply about vacuum. So we work not with matter, but with vacuum. However, we work with the so-called electromagnetic vacuum. So, and better to say electroweak vacuum, maybe better to say like this. So official title here is Solidifying Vacuum for a structure of the electroweak model in a strong magnetic field. So clarifying title, jokingly, should be like that, but it's precise. So I will talk about solidifying and evaporating vortex solid liquid, which is made from nothing. Here, nothing means vacuum. So you cannot make less nothing than vacuum, which possess superconductivity and superfluidity at the same time. Superfluidity and superconductivity and superfluidity means that we expect that matter or energy can move in dissipation manner. And we need only one simple ingredient, it's a magnetic field. So the only thing we need, nothing else. So if you would look to this first title, you would say that it's unbelievable and surely it's one should put it in some yellow press. However, these results are based on the paper which actually was published last year. We have some new results, but basic material here is from this year. It was published in physical review letters. And it took us approximately 2 years to get them, basically numerically. However, some signatures of those effects were seen before. So the idea is that whether we can get something non-trivial from the vacuum, like superconductor, just applying only magnetic field. And this idea also sounds, I would say, controversial because we know that magnetic field and superconductivity, they are enemies. So they don't like each other. We know that there is Meissner effect, which kills superconductivity. And we know that magnetic field, no, Meissner effect, strong magnetic field kills superconductivity, while superconductor repel magnetic field via Meissner effect. So these are the same kind of some sides of the same coin. So they don't like each other. But here I claim controversial statement that in fact, you can use superconductivity, you can make superconductivity out of vacuum and make some non-trivial structure of the vacuum just using magnetic field. Okay, and then, of course, one can ask what kind of, I'm sorry, what kind of magnetic field we should have, in fact. Let me just very briefly go through fields, through the scale, and then stop at the field which I want to choose for my discussions. Okay, first one is 1 Tesla. It's not a car, it's just a reference frame for us. Just you can find a loudspeaker or NMR imaging. Here we have approximately 2 Teslas usually. So it's just basic scale for us. Then we have, since we're interested in field theories, the next frontier for us is QED scale. So QED scale is just basically given by mass of typical particle which participates in the process. In this case, it's electron. So we take electron squared divided by elementary charge and get approximately 10 to 9, 10 to 10 Tesla. The Schwinger scale and such kind of field exists, believed to exist at the magnetar surfaces, and even larger field can exist in cores of magnetars. Here is a little bit of speculation. Also, here is more or less known, I would like to say. This is speculation, but still it's quite reasonable. And those magnetic fields, vacuum acquires optical birefringence properties, so light changes velocities depending on the orientation, polarization polarization of the incident photon with respect to magnetic field. And this is an example in the quartz crystal, at which you see that the lines become a little bit shifted with respect to each other because this coefficient of refraction becomes different. And vacuum can also act as magnetic length due to this property or similar properties. It just basically a little bit similar to gravitational lengths, which start to distort the image behind it. And that happens, one can understand it as basically light by light scattering. So we have light just which comes, creates some box made of the virtual electron or electron-anti-electron pair, and then goes further. So it's just basically light by light scattering, and this light by light scattering leads to such kind of nonlinear properties, which we call lattice birefringence. Okay, sorry, optical birefringence, yeah. Then the next statement is that next scale for us beyond QED, this is QCD. QCD, quantum chromodynamics. In quantum chromodynamics scale, the typical mass is mass of the proton. Formula is the same. So we take proton mass squared divided by electron charge and by elementary charge. And then the typical fields here are 10 to 16 Teslas. Those fields, many things can happen. There are a few, just to mention a few, that first we have magnetic catalysis, enhancement of chiral symmetry breaking in zero temperature, and inverse magnetic catalysis, depression of chiral symmetry breaking at high temperature, which is actually not understood right now at all. It's numerically observed, but people don't understand it very well. And there could be also vacuum superconductivity, but it's different story because it's based on different particles. I will not talk too much about this. And such fields can exist in heavy ion collisions. We can create them. However, for a very short time, it's like 1 octosecond. So 10 to minus 24 seconds, which is actually not big scale, I would like to say. So it's transient field, very short. However, they're accessible here on the Earth. And next scale for us, about which I will be talking about, is electroweak scale. So electroweak scale is just given, again, formula is the same, but take typical size of the typical mass of the particle, so typical scale of the mass which is involved in the theory. In this case, it's W mass. So take it squared, divide by elementary charge, and we get again higher field. It's 10 to 20 Tesla. So that's the field we'll be talking about in this talk. So, and in fact, that's quite interesting field. So people discuss that it could have appeared in early universe here. So in principle, but many things can happen in early universe since we don't know if we can hide everything there. So that's why it's not actually certain whether such field existed there or they have not existed at the beginning of the early universe. And the interesting point here is that at this field, we should get some change in vacuum structure. So it means that the vacuum becomes different. There could be new phases. That just theoretically, it was interesting at some point. So what happens if you apply a very strong magnetic field to the vacuum? That's basically will be the interest of my talk. However, you can ask the question why I'm talking about that, because in fact, okay, it's not really certain what we'll get there. Moreover, it's not certain whether it's early universe, we will have some other conditions, for example, like not only stromagnetic fields, but for example, high temperatures or high densities, which can destroy all those effects, which I will be talking about, because I will be talking about vacuum, not about plasma. So, and I would like to say that, in fact, we have examples, at least theoretical examples, where such field can exist, maybe even now. We don't know. These are speculations. So these are ideas which were in the air for many years, but they were nicely formulated during coronavirus time by Maldacena, who made this very nice corona picture here, just the right time, the right picture. That's the picture of the following, that if you have a magnetic, highly magnetized black hole, Then if this the magnetic charge of this black hole is high enough, then you can get a quite interesting atmosphere around this black hole. So it means the following, that usually one can assume like that. So you have, for example, some black hole, which created during early universe, or say nowadays, imagine, of not big size. And then this black hole just finds some monopoles around. Okay, nowadays it cannot find monopole, but imagine that it has been created at early universe and survived. Then it ate a lot of monopoles, and more monopoles and anti-monopoles, and then just it becomes magnetically charged. So it got hair, those hair are magnetic, and the magnetic hair just will go outside of black hole. And in that sense, this magnetic black hole could be seen like a multiple charged monopole. However, multiple charge monopole is unstable, in particular because its core becomes too energetic. It's like basically multi-charge electron or multi-charge system. If you put too many electrons in the same point at the fundamental scale, say at the distance of many small fractions of Fermi, they will just basically will be repulsive too much. The system will decay. There will be too much energy inside. However, if you hide it behind the horizon of the black hole, then the system gets stabilized. At least we hide this divergence somewhere behind horizon. So we can see only the magnetic fields. And those magnetic fields, when they come out, they form some strange regions, two types of regions of this kind or that kind, about which I will be talking about. I will show it a little bit later, where electroweak symmetry is restored, and where we will have some vortex, liquid, fluid, superconducting, superfluid phase. That's about which I will be talking about as well. So Maldacena just speculated that we should have this two-phase structure, and right now we understand how it should be looking. Exactly. Okay, more or less, I would like to say. Okay, so I would like to say that such objects exist at zero temperature, and in principle, for us, it also gives some motivation to study this particular topic. And there are also papers, I show one of the examples, which say that in principle, you can have such fields depending, this is just magnetic field here. Here are the limits of magnetars, highly magnetized neutron stars. Here are the pulsars, normal neutron stars. And here are just two different critical fields corresponding to the restoration transition of Higgs field of electroweak symmetry, and also of this another phase, which I call superconducting phase. So I will describe it a little bit later, but I would like to say that those lines, and this is magnetic fields here, they're quite nice. By the way, here is on the horizontal line, I think it's clear from this notation, that's mass of the black hole as the measure of, in terms of sun mass. And here is approximately the mass of Earth. So basically, I would like to say that interesting black holes for us would be of the mass, like 1/3 of mass of the Earth, or a little bit smaller. But I will not be talking about black holes. Yeah, I'm talking about layers around it, which we could observe in the absence of gravitational field. Just first our attention, just to show what we can have the simplest case with the vacuum. And then we can later apply and look how it would look in the case where magnetic field is actually surrounds some gravitating object like a black hole. For just to have an idea of the sizes of the objects, that typical black hole radius for 1/3 of mass of the Earth, black hole of this mass would be 1 centimeter, and this vortex superconducting atmosphere, so this layer would be approximately 1 millimeter. And this is also the same approximately size. So it's quite human size. The only mass is not so much human, I would say. So in fact, the change of vacuum in electromagnetic field has been understood and been discussed many times. Has been discussed semi-classically, or I would like to say classically. So there is, as I said, there are ideas about QCD scale associated with Rho-Meson condensation. I will not talk about this; it's additional topic, but I will mention later. I will talk about this one. So for me, this work was motivating to study this research. So ideas appeared a long time ago. We see the years, even before, maybe 10 years before people started to talk about this. So they just basically applied magnetic field to the, just consider it to the vacuum, basically consider it electroweak equations of motion, classical equations of motion in the case of background magnetic field, solved them, and found some non-trivial structure at some particular value of magnetic field. So they found inhomogeneous condensation of W bosons. I will talk a little bit later about them. And everything looked classical, easy, and undisputable, because, on classical level, just everything should be simple. In reality, it turns out to be not the same, as not actually correct what's written here. So it's, first of all, it doesn't look like classical. Second, it is not easy at all. And third, it was disputable, because people tried to find this phase and they could find nothing. I mean, numerically, just for principal simulations, they found just nothing. Okay, let me just explain the idea, how it works, why we should expect something non-trivial. So imagine, just very briefly, for a second, imagine that you have a free particle, which doesn't interact with anything except for background magnetic field. Magnetic field is static, uniform, and occupies all the space. And the particle has a spin S, and you just put it in magnetic field and solve relativistic equations corresponding to the particle, or Dirac equation, or some scalar equation and other for vector particles as well. And generic formula for the energy of this particle in magnetic field will be like this, just exact formula. So here is Pz is the momentum of the particle along the axis of magnetic field. N is non-negative integer number, which basically labels Landau levels. Here, Sz is the projection of spin on the magnetic field axis. And this is magnetic field, which this formula I assume to be positive, so E times B is positive, and m squared is the mass of the particle. And one should mention importantly that here I assume that gyromagnetic ratio here is 2. So here, this 2 corresponds to gyromagnetic ratio, which is basically correct for Dirac fermion. It's also correct for non-abelian W boson, actually. It's abelian, but it comes from non-abelian group. So it's for non-abelian particles, it's also correct. Also, they have abelian symmetries after symmetry breaking. Yeah. So, and if you look to those fields, then you can say, okay, let's right now consider, for example, the particle. Say, for example, if you consider the scalar particle, then S is equal to 0, then lowest level is given just by 1 here. So this is 0, this is 0, and then we'll get that magnetic field will increase the mass of the particle. It will be just because this Landau level fluctuations, 0-point fluctuations of particles will depend on the magnetic field, and there will just mass will be increasing. So you can assume that you have just particle which moves only along direction of magnetic field at lowest Landau level, and EB corresponds to effective mass, or you can say effective energy at rest frame. They will be the same. So if you put fermion, you put here 1/2, and then at 0 Landau level, so lowest Landau level, this will be 0, and this 1/2 gives, with 2 gives you 1, and with minus it cancels this one. And that's why you get the energy of the lowest Landau level, independent on magnetic field, up to Zeeman coupling, which we ignore here. I mean, anomalous Zeeman coupling, anomalous Zeeman interactions, which we ignore here at all. So in this case, one can see that we'll get basically nothing but Landau level degeneracy, which is famous for many people. I mean, we just get the, which is very well known because it leads to Hall effects and so on. Now let's move further. Now let's consider charge 1. Okay, charge 1 particle, of course, charged, and spin 1. So spin 1 here gives -2. So lowest Landau level corresponds to S equal to 1, Sz equal to 1. So this gives you -2, unity -2 gives you -1, and you get immediately that here you get minus sign. And that's already some interesting point, because EB is always positive, as I said, and you get the following mass of the particle. So you get that in magnetic field, mass of the particle will decrease. not only actually mass of the particle, but mass squared of the particle. So it means that at some particular value, the mass of the particle will vanish. And then if you increase field a little bit further, mass squared of the particle becomes negative. It means that the system becomes unstable. And you should experience something like a Higgs mechanism. So there should be some symmetry breaking or something like that. And for W bosons, this effect happens at characteristic scale of mass of W boson squared divided by E, as follows from this formula, and it's approximately 10 to 20 Tesla, exactly as I discussed before. So in principle, we should get a kind of W condensation in this magnetic field using this very simple analysis, just without solving any equations, except for solving free particle and Landau levels for free particles. That's all. Of course, one should put then correct equations. I will show that a little bit later. So it was suggested that there should be condensation of W bosons. It was a long time ago known. Then I found that it should lead actually to superconductivity properties. So also the system would look like superconductor. It is not superconductor. Actually, just if you look to that, it becomes a very strange superconductor because it's superconductor not in usual sense. So it's will be anisotropically superconducting. So it means that it will superconduct only along Landau levels, or better to say along magnetic lines of magnetic field, sitting on the lowest Landau level. And due to that particular fact, the system does not possess a Meissner effect. So Meissner effect appears because of free superconducting current, which are large currents, which attract external magnetic field. And in this case, there is no way for those currents to form because the currents are just moving only along the lines of magnetic field. So you cannot screen with those currents external fields. And that's why it will be a very exotic superconductor of anisotropic type, I would like to say. So it's not usual superconductivity, which would not have Meissner effect. So superconductivity of the vacuum is interesting and quite non-trivial phenomena. And of course, one should assure that this effect exists because at the moment it's just only hand waving basically and some classical equations. So that's the aim of this talk, just to study whether we have this phase of W condensate and how it looks like. So now let me just come after this motivational part. Let me come quickly to the main structure of the talk. So the suggested structure of the vacuum is the following. So we have ordinary vacuum up to magnetic fields given by W scale, mass of W boson. Then we get superconducting vacuum. Then there are many speculations that at the mass of that, at the magnetic field of the mass of the Higgs boson, so EB equal to mass of the Higgs boson squared, there should be another transition where superconductivity must be restored. Okay, superconductivity. Sorry, I did it that. It's not superconductivity, but electroweak symmetries should be restored. So superconductivity should be destroyed, but electroweak symmetry should be restored. So there should be basically some massless particles should appear in the spectrum. Also, it's also questionable. I will mention it later a little bit. And this phase attracted attention for many people for a long time. It started by Nobel Prize winner Salam a long time ago as well. And then also Lindy discussed a little bit later. And there are many recent efforts. There are many papers on that. People speculated what happened here because it was totally unclear what happens really at magnetic field. And actually, masses of W boson and Higgs are quite close to each other. So they're not so much different, at least. So that's why those phases should be quite narrow placed according to general scale of all hierarchy of all masses. So that's why it's in principle they're accessible close to those black holes, and it would be interesting to see whether we have this phase or not. And now I talk about setup. So we would like to check the structure. And our setup is extremely simple. So we take electroweak Lagrangian, and we take it without fermions, because fermions don't play any role here. At least quantitatively, they don't play any role. Qualitatively they play no role. Quantitatively they play, but maybe a little bit. So I would not say that they do some major contribution here. So we don't expect any change from them. They can a little bit shift constants and so on, but change should be quite small. So we take this Lagrangian. Lagrangian here consists of 4 pieces. One of them is basically an abelian part, Higgs field interaction with those two parts through the long derivatives, and also potential for the Higgs. Abelian, non-abelian, and abelian part, these are field strengths for non-abelian gauge field and abelian gauge field, which due to symmetry breaking governed by Higgs field just leads to the standard of symmetry breaking. So we have SU2 times U1 is broken to U1 electromagnetic. And after symmetry breaking, we recover standard particle content of the theory. We have W bosons, which are massive charged vector. Then Z boson, which is massive neutral vector. We have also photon, massless neutral vector. And we have Higgs particle, massive neutral scalar. Here I say neutral charge with respect to electromagnetic field A. So these are our particle content. And basically, what we should expect here is the following. That's theoretical results. These theoretical results were close to critical temperature. Critical magnetic field. So everything is here. It's 0 temperature, of course. So we, again, take the theory, solve right classical equations of motion, apply background magnetic field, solve those equations, classical equations of motion and magnetic field, and then the just look and plot what we get. So here I plot average W boson condensate, and it looks like this. So when we move just to magnetic field, it's a little bit lower, it's 0, and then we have clear second order phase transition. We have here many lines. They correspond to different masses of Higgses, just to give you impression what would we get if you would have different mass of the Higgs, because this paper was written at the age where Higgs has been discussed, basically, its mass. So 125 corresponds to correct one, and you see just typical second order phase transition here. Looks nice. Then mass of the Higgs will start to go down with magnetic field. But please notice the scale here, it will go down slightly, linearly, but slightly down. So one can see that the emergence of the W boson condensate starts to depress Higgs condensate. And we'll see that this actually feature quite local. Energy ground status also goes down. And one can also determine so-called density of superconducting pairs. That's basically determined by second London equation. It says that how fast the current emerges due to applied electric field in superconductor. So you have superconductor pull electric field, and you'll get ballistic acceleration of the electrons there, or superconducting pairs, basically electrons in superconducting pairs. And seeing how much current is induced, you can get knowledge about superconducting condensate, how big is it. So this is quantity is plotted here, and we see that it also increases with the magnetic field. So, okay, that's theoretical picture, but that's only part of it, because in fact, it's more complicated. Before I've shown you average values. In reality, Higgs, the W condensate becomes quite complicated. It shows vortex type structure, which reminds the second type 2 superconductor in the Abrikosov phase, or this mixed phase. That's why people say that it's similar to superconductivity before. But in reality, it is superconductor, but very strange. So they form hexagonal feature here, so similar to type 2 superconductivity, typical one. Here are pictures supported just theoretically solid in perturbation theory at just field which is 1% higher than critical field. But the interesting point which appeared here, this is this paper, is that in fact inhomogeneities in W condensate lead also to inhomogeneities and induction of the condensate and inhomogeneities in neutral condensate. So we see this kind of, I call it two-step structure in the Z condensate. So it also appears here. And yeah, by the way, I cannot say that, but just I think maybe it's clear from the pictures. In these pictures, we plot the condensates or all quantities, but they are plotted in the plane which are perpendicular to magnetic field, normal to magnetic field. So magnetic field basically goes somewhere in the direction, and here is direction x1, x2. So this particular plane. But here in these pictures, I plot particular quantities like W condensate, Z condensate, and Higgs field. So this Z boson, it's also, you see, it has some very interesting structure, and it's actually is maximum where the derivative of the W condensate is also takes its maximum. So it's approximately like that. So it's given by the homogeneities in the W condensate. And if you look here more carefully, you will see that there are some points very similar to those points here. And those points, those kind of tips, they correspond to superfluid vortices. So if those are superconducting vortices, but those are superfluid vortices. And then we can also say, okay, right now I would like to understand what's going on with the Higgs condensate. And this is Higgs condensate. Here is a red line here corresponds to the Higgs condensate without symmetry breaking. And here we plot usual Higgs condensate, which is solution of the classical equations of motion. And you will see that the Higgs condensate gets suppressed. And it's actually suppressed more where W condensate forms. And where W condensate vanishing, that Higgs condensate is trying to get more. So they don't like each other. The bigger the W condensate, the smaller is Higgs. That's why it works nicely. So you get increased magnetic field, you introduce W condensate, and W condensate suppress Higgs field, and Higgs field should eventually die at strong magnetic field. That's why we should get this phase. But things are not so much easy, but naively it looks like this. Okay. If you, let's say, flash this transparency quickly, because one can tell hours about this. So that's how vortex picture looks like. So here, those points, hexagonal points, these are superconducting vortices mainly. Then you have also superfluid vortices. So they are blue and green corresponds to superfluid vortex and anti-vortex. Then red correspond also to the vortex in the W phase. And here, yeah, and again, you see that those vortices coincide. So you have superfluid vortex on top of superconducting vortex together. And those lines, these red lines, oh, sorry, white lines, they correspond to the cuts basically in the phase, because here color, they correspond to the phase from minus pi to pi, and then the jumps between the phases, the phase and the condensate, they correspond to these Dirac lines, basically. This here, the condensate is visualized, phase of condensate visualized for W condensate. And here is the same picture, basically vortex picture, the same here and here, but the phases are visualized for the Z boson condensate. So you see, pictures are quite beautiful and structure is quite unusual. So if you then ask me where actually superconductivity and superfluidity goes on, the picture looks like this. So it's here the regions are corresponding to positive vortex, okay, like that, positive superfluid flow and negative superfluid flow. So you have here green and red that correspond to superfluids, and those lines which are blue, they correspond to superconducting flows. So I say positive and negative because if you have some excitation, you can excite both positive and negative flow generally. So they will work in opposite directions. So basically these two regions, these two colors, red and green, correspond to superfluidity, and the blue correspond to superconductivity. So the model again is very simple, but the picture turns out to be rather complicated. And it's physically very different from time to superconducting, so just superconductors. So, and I will also show them later why it is drastically different. Now I come to results lattice simulations, because this picture is classical, it has to be confirmed. So I will flash transparency very briefly. What we do, we put system on the lattice. We just discretize it, put on the lattice, introduce some link fields, some gauge connections, make Wilson action, then consider action made of many parts, say gauge part, Higgs part, interaction between them. We take a rather large lattice, put magnetic field along the directions. We put many types of magnetic fields just to make sure that we understand system correctly. We have many parameters here. which corresponds to background magnetic field, physical couplings, and also size of the lattice. So, and I would like to say that pioneering study in this direction has been done by this group. 25 years ago, they found nothing. They could not find any nice, interesting structure. They found something, but very different, and so surely not what has been predicted by the theory. And but they were working at relatively high temperatures. So our idea was that probably they looked at the phase where the condensate already melted, because temperature destroys everything. Okay. So then we are sure that we have physical point, again, flash transparency. So this is physical values of Higgs mass, Z mass, W mass, values of couplings, which we know from electroweak model. We are sure that we are very close within 1% of physical value. It took us really 2 years. I mean, during COVID time, it was quite complicated. So just to find point, because we need to find one physical point in the 4-parameter space. It's really, and every point takes a long time to measure. So, and finally, we decided not to work with magnetic field, but with hypermagnetic field. They are actually the same in the system, in the phase where the symmetry is broken. Electric symmetry is broken, so it means that normal phase and superconducting phase, they're basically the same. So By is equal to B with corresponding couplings. This is hypermagnetic field. So it's magnetic field corresponding to basically to U1 genuine U1 part, not electromagnetic, but this original X field of the electroweak group. Why I say so? Because since we would like to go to the symmetry-restored phase, in that phase, the sense of magnetic field loses sense in some way, because magnetic field is defined by direction in isotopic group of electroweak theory, and basically by direction of Higgs field in this SU2 group. And if Higgs condensate of Higgs field doesn't exist, or it's frustrated, then magnetic field will also be frustrated. So there is, I mean, no good definition. But hypermagnetic field exists, and in interesting phases for us, for superconducting normal phase, it just usually kind of expressed through magnetic field, and after that, okay, it becomes a genuine field which is exists without any magnetic field, because, okay, as I explained. So it was a difficult task for us, so we worked with this field. So, but I will show our results in both fields, in magnetic and in this one. So, and that's our result. So, again, here is the theory. So we should get ordinary phase. Then it will jump to superconducting phase at mass W. And then this phase should disappear at mass of the Higgs. And we get symmetry-restored phase. Here is our picture. Here we have condensate. Higgs condensate, it's normalized Higgs condensate in units of Higgs condensate at zero magnetic field. So it's approximately does not change, and then it goes down and then disappears. And indeed, we see two different transitions. Fine. There are two things. First of all, there are many interesting features here. First of all, I wanted to say phase transition, but it's not phase transition. It looks like extremely smooth crossover. And even if maybe it's not even not a crossover in the usual sense, because normally if you have normal crossover or transition of the second or the first order, you will always see some peak in susceptibility on the finite lattice, in the finite volume. So in this case, this is susceptibility of normalized Higgs condensate. And you see that instead of peak, we see just kind of increase, and then we see some structure. Here, just plateau and then decrease of this quantity. So we don't see any peak which would characterize as any of the condensate. Maybe there are some higher Binder cumulants which will be non-zero or other statistical quantities, but we see no phase transitions here. This was first surprise. And the second surprise, yeah, and actually I started with the second. But it's interesting theoretically, because classically transitions must be of the second order, as I have shown you. Then there were many discussions, and I just quote one of the papers here, that the transition should be actually stronger, should be of the first order. But we have found it actually it's of infinite order, effectively, so it's just a crossover, it's not transition at all. So theory contradicts experiment, or I would say numerical experiment contradicts theory totally here in this sense. And a second thing that what was surprising that the first transition actually it was shifted. So it is not actually at mass of W, but 30% lower. But it's okay. We always expect some quantum corrections can normalize our values. But what is most even surprising, the second transition, which is restoration, is just exactly what was predicted within 1% or 2% if you take into account the error bar. So just exactly the Higgs of the mass, which was predicted by Salam, Linde, and others long time ago. So that's actually for us was surprising. Okay, so this is picture. Now you can ask how vacuum looks like. That's our general view. So here I show you, so this is magnetic field. This is magnetic field given in terms of the condensate. Yes, okay, so in terms of condensate. So here is, okay, let me just repeat. So here I show Higgs condensate. This is another curve corresponds basically to effective quantity, which is average action, basically demonstrates that our results are getting invariant and nice from lattice point of view. But I would turn attention to this curve. So here we have one phase, another phase. So this is normal phase, superconducting phase, and symmetry-restored phase. And here I plot cross-section perpendicular to magnetic field of, in this case, of Z flux. I can put any quantity, almost any quantity that will show similar structures, but this particular one was actually quite nice to show because it was really, I mean, very well seen. So these are typical configurations which are taken on the lattice and we make snapshots. And then we increase magnetic field strength. We see that first of all, we see some noise in these configurations. That's actually this at zero magnetic field. Then close to the transition point, we see again noise. And then once we a little bit below jump over this magnetic field, we will see here some structures appears. Looks like kind of lumps, like maybe we could say vortices. But then as soon as you increase field further, you will see that vortices again forming. And then here you see clearly that there are some kind of vortices. I say vortices because it's a cross-section of the three-dimensional space, basically. So structure should be one-dimensional along magnetic field. So you see this kind of structure, but if you look carefully, you don't see here hexagonal structure. Let me just jump quickly. You see here, this is classical picture. Here you see there should be kind of hexagonal graphene type of structure of vortices. And in this picture, we don't see them. We see vortices do exist. Some of them remind us some kind of hexagonal type of location or triangular type of structure, but it's not actually the real regular lattice. And then if we increase further, then we see that number of vortices is increasing because indeed it's the same physical surface here, the same physical size. So magnetic field increases, number of fluxes increases, vortices become smaller because Landau levels becomes tighter, and physically, I mean, dimensions, and therefore vortices form kind of chains, you see, or pairs, but they will decouple, you will see. Then they start to form some other objects, which I don't know how to name, but I will show also later something. Then will start to melt due to fluctuations, and then they disappear again. So we have again fluctuations. So here we have symmetry-restored phase. So picture is quite interesting. And then if you look, for example, how the vortex condensate forms, here are just the result of simulations. You can see that, for example, if you take some regions here, say red and green regions, here on these two pictures are the same, just to guide the eye, you will see that those fluxes here on the vortex, they form around, and they correspond here like to circulation of perpendicular or normal Z vortex, Z currents, so Z charge currents, Z boson currents. So it's like in usual superconductor, I would like to say you have some vortex and the currents will be circulating around it. So it looks similar. Now let me see how this picture looks like when we just move along this line, just to make it, just to see how it's visualized. So we just here increase magnetic field, and you see up to now we had only fluctuations, and then as we move to the new phase, we see that vortices start to appear, but they move. You see the interesting point, then they move. I just jump from configuration to configuration, and I see that, or within the same configuration, move this time slice, and I see that they are not standing. They are kind of like a liquid or fluid, but better to say liquid. They are moving. They are moving, and until the point that we come to the next phase, and then this liquid evaporates basically. This liquid evaporates, and but it's a zero temperature with magnetic field, and then we get noise. So that's quite interesting picture, which I would say that for us was quite unexpected. And there is another feature of that, because then you can call it like it's fluid. Let me just run again and turn attention to another feature, which is not very visible in this very short movie. So there's another feature. The interesting point that it is similar to the fluid, vortices are moving. But contrary to the fluid, vortices are moving within their cells. They don't exchange their positions, so they don't intertwine. It's obvious from the point of view, because vortices are, they are kind of spaghetti. It takes some energy to change completely. But if you look to cross-section, you would not say that it's kind of two-dimensional fluid. It's no. It looks like a two-dimensional disordered solid, I would like to say, if one talks about cross-section. One speaks about cross-section, right? So so I'm just going to the end of the talk. Another shock here is the following. So, okay, now let me just do a few things which are kind of good and kind of they have interesting features. So here the first line corresponds to theory. So first row corresponds to theory. Another row corresponds to simulation. So I took theory from my old paper and simulation from new paper. So what is shown here? Here we show W condensate, Z condensate, then changing Higgs condensate. Higgs still is non-zero, changing Higgs condensate, and variation of magnetic field. So magnetic field in our case is dynamical as well. It means that it adapts to the condensate and so on. So it's also important to understand it. It's very important that it feels free, democratic. And then here in all those pictures, so let me first go through theory. We say the following. So we choose two different regions just to guide an eye. I put them. These pictures correspond to the same theoretical solution. We have red and green regions, especially put together to guide an eye, and they correspond to the same part of space at all pictures. So then one can see that indeed we have here W condensation, and W condensation appears where we have red regions here. Here W condensation. At blue points we have condensate dumped, and in that part we have superconducting vortex. Okay, we have vortex, better to say. Then one can see that homogeneities of W condensate lead to Z condensate. We have kind of those rings, which I have shown you before in 3D picture. Okay, fine. Then we have Higgs condensate, which feels itself better if there is no W condensate. Indeed, where we have blue, so no W condensate, we have, yes, so a lot of more at least of Higgs condensate. But what interesting happens is that magnetic field tends to be depleted in the center of the vortices, superconducting vortices. So it's kind of, it was called before anti-lens effect, and it's related to the p-type of the superconductivity, spin 1 superconductivity. I'm actually basically coming already to the end of the talk. So you see, it's normally in type 2 superconductor with scalars, type 2 superconductor, we would assume that this magnetic field, which makes hole in superconductivity, or superconductivity allows the magnetic field to penetrate in terms of vortices, and inside the vortex we have highest magnetic field. Here is vice versa. We have the condensate, and where we have the superconducting condensate, we have sorry, increase of the of magnetic field. And in the places where there is no superconducting condensate, so no double condensate, we have decrease of magnetic field. So the structure is completely different from what we could expect. It's related to polarization of spin of W condensates, but it's quite unusual from the point of view of normal superconductivity, standard superconductivity. Now I do the same thing. I just take a simulation. I took typical configuration. We really specially took just general configuration because all of them are the same. All of them are the same good, I would like to say, or bad. We took one configuration and we get the same. So we also took two regions. We two configurations which are approximately similar to this one. So they have kind of here 2 points together, here 3 points together. And we see that pictures are approximately the same. Here we have actually two like vortices. Here are 3 vortices. They're a little bit blurry because, you know, as I said, we have fluid or liquid, better to say. We have liquid or disordered solid. They vibrate a little bit, and that's why they are a little bit blurry. Here, for W's, for Z bosons, we have smaller structures here, similar to this one. Also, they are not round, but they are kind of interacting with each other. Higgs condensate is again increased in terms of in the center of W condensates. And magnetic field again is decreasing the center where W condensate is depleted. So it's, yeah, so we have really good agreement apart from the fact that the theory is not, doesn't give you crystal structure. So I'm coming basically to the end. So here I show the numerical simulation result. So I will show you cube. So now it's 3-dimensional part. Before I have shown 2-dimensional slices. Here we take 3-dimensional part and we visualize 2 things. Actually, it will be third one, but 2 important. One of them is W condensate. It's given in blue. And also Higgs condensate is given in the green color. And yes, and actually here there is red. That's the part, I think, where this W condensate is highest, maybe like this. Yes, yes, yes. So basically, it's equipotential surfaces. You will see that just give you geometrical expression how they look like of the Higgs condensate and of the so green and blue is the W condensate. Yes, and then you will see also lines which denote this hypermagnetic field, which in this case it's magnetic field as well. They coincide together. Okay, and then I will show, and the picture will rotate, and I will remove one condensate and another condensate and put them together just to see how it looks like 3-dimensionally. So here is W condensate is removed. You see Higgs condensate, which lives outside of W condensate. Then if you remove Higgs condensate, and yeah, you see it's like that, and you will get a W condensate. And you see there, and here is the ferromagnetic field lines. And you see that interesting point that they looks like, you see, they looks like parallel to each other, a little bit wiggling, but mostly parallel to each other. Also, they don't really kind of like tubes, you know, they're not rigid. That's why it looks like more disordered spaghetti fluid. I don't know. One should invent a good name. Yeah, so we see this kind of picture. We see this type of picture, except for this one, I forgot here to say, is forbidden. We never saw any kind of twisting and bending. Also, it's possible. We see something like this situation in our case. So it's like, okay, you see twisting. Yeah, everything depends on the angle. Let me show you Weinberg angle. We can ask you whether this picture is generic for this class of generic class of the electronic theories, because there are many parameters. You can check them, maybe you get something different. And yes, it's very specific for physical parameters. If you take different parameters, for example, take so-called semi-local limit, so it's different Weinberg angle, then you get their completely different picture. Here are earlier results like this. This is Higgs condensate. And you see that indeed we see vortices here at some particular value of magnetic field. So in this superconducting phase, you see they are vibrating a little bit, but basically it's hexagonal. So if you look at carefully, it's vortices are a little bit quantum. There are some quantum fluctuations. So you cannot say that it's kind of fluid or liquid. It's more or less regular structure here, a little perturbed by quantum fluctuations. Yeah. So the value of physical parameters is important, in particular 5 Weinberg angle to really to get physical picture. So now I'm finishing. Let me just repeat very quickly what we observed. So we were first to find this structure of the electronic theory at 0 temperature. At strong magnetic field. So that's first thing. Second thing, just on the lattice. First principle numerical simulations, because there are some attempts and people could not find it. I know there are published work, quoted one, there are many unpublished, people tried to find, they could not. That's just because of technique and parameters. One should have large lattices, good algorithms, and so on, so to get rid of noise. By the way, I would like to say that what we, from lattice point of view, what we did genuine lattice simulations, Monte Carlo, hybrid Monte Carlo, and we have not used any cooling or smoothing, nothing. We just, what I have shown, just its real configurations without any additional efforts, basically. Yeah. Then we observe this picture, which has been predicted, phase structure, which is predicted by the theory. So the first phase a little bit shifted towards lower fields, like 30% smaller, but doesn't matter too much. Then vortices, what we got basically prediction coming from Ambient-Wollesen solution. I forgot to mention these people, but I have shown them. They first found this solution in explicit form. So no crystal lattice formation. We have fluctuating vortex medium. And we have no phase transitions. We have smooth crossovers, which was a surprise to us, and these are even not real crossovers. We have no peaks in susceptibilities. Probably that's due to because in the intermediate phase we have the classical objects basically from the vacuum, which increase susceptibility, increase fluctuations because they're classical and they are moving. That's maybe the reason. Yes, and I would like to say that similar transition, or not transition, I would like to say, but similar picture actually have been seen in quenched QCD on the lattice long time ago, like 10 years ago. It was just only one publication on the list. There are such kind of features in lattice QCD at also high temperature. Oh, sorry, high magnetic field. Yeah, but its study hasn't been followed further because for QCD, such simulations are increasingly more complicated due to the dynamical nature of fermions. Okay, I hope that I'm in time. It's 95. Okay, 95, 59. Sorry. Thank you very much.